Hello, everyone. This is Wenbiao Han from Shanghai Astronomical Observatory, and today I will share my recent work about to test the WEP, the weak equivalent principle with the binary black hole events from LIGO. And first, I want to thank you very much to give a chance to share our recent work at the great network, and this work is in collaboration with my PhD student Yang Zhuchen and Dr. Wang Gang. Okay, about 400 years ago, Galileo did an experiment. Maybe he didn't do this experiment, but some story said, okay, Galileo did this experiment at the Pisa Tower, and to prove the two bodies with different weights will be arriving on the ground at the same time if you free fall at the top of this tower. And after sometimes, and this experiment is get a principle in the physics, very basic principle we call WEP, weak equivalent principle. It's mean that the mass or initial and the ratio between the initial mass and the gravitational mass should be a constant for every body in our universe. And then it will be give that the result that, okay, if you free fall two bodies in a gravitational field, they will have same acceleration. And this is the foundation of the curve of the space-time. And this is the key idea that takes the gravitation of the curvature of space-time in the general relativity. So in principle, we can say that, okay, WEP is a basic stone of the general theory of relativity. And the equivalence principle have three kind of variation. First is the WEP we just discussed. It's just very simple. If you drop in two different bodies in a gravitational field, WEP states that the bodies fall with the same acceleration. And after WEP, we have an Einstein equivalent principle. It's because that they add the local Lorentz invariation and local position invariation. And it's meant that if we have a local free fall frame, local free fall coordinates, and in these local coordinates, every physical experiments should be same with the result of the spectral relativity. And so Einstein equivalence principle should be a foundation of any for the curve of the space-time to explain the gravity. And after that, we have strong equivalent principle. And the strong equivalent principle is actually exactly, we can say it's the foundation of the general relativity. Until now, we have a lot of experiments to prove to test the WEP by free fall. For example, we use atom in the vacuum to observe the free fall of the atom, and we use the LLR, lunar laser ranging. We use these experiments to test the WEP on the ground in our solar system, and we achieve at a very high accuracy. For example, 10⁻12 or 10⁻13, something like this. And for example, this is we use loadless ranging to test WEP because that the distance between the moon and the Earth will be changed if WEP violation, because the moon and the Earth are free fall towards our sun. Okay, so we have these equations to see the distance between the moon and the Earth with this parameter, and this parameter is come from a lot of other parameters we call the parameterized post-Newtonian parameters, just or shortly say PBN parameters. Okay, we should remember this gamma is it will give an effect that the time delay or light or time or light deflection, and the absolute value of the gamma now are measured by the BBH or Cassini tracking at the 10⁻⁵ level. Okay, but all these experiments are done in our local space, for example, on Earth or in our solar system. But maybe we can ask that, okay, if this experiment in the cosmology scale, how about the result? Or what we can ask that, does the WEP also are valid? Is WEP is valid in the cosmology scale? So there are also some free fall experiments in the intergalactic scale. And usually we use some astrophysical phenomenon, because the astrophysical phenomenon will radiate different photons with different energy, or neutrinos, or gravitational waves, and passing through the universe is especially pass through the gravitational field of our galaxy. So we can say that here this is a time delay, not due to the Shapiro time delay, but due to the difference of Shapiro delay of the different free fall bodies. Exactly, this is free fall the massless body particle, for example, photons, gravitational waves, and maybe sometimes they think the neutrinos. Okay, so this potential is the gravitational potential of our galaxy, or maybe we can add the potential of the host galaxy where the source radiated. And the gamma 1, gamma 2 is for the different photons. For example, for the photon with 4 GHz, they have a PBN parameter gamma 1, and for 5 GHz, they have gamma 2. And if these two gamma is different, they will reduce. They will give reduce time delay come from the WEP violation, and this will be observed, can be observed on Earth. So we just change a little bit of this equation, and we can test the delta gamma is equal to this delta t, and over this the integration of this potential. And if WEP is valid, delta gamma should be 0. Be careful, this is not to test the absolute value of the gamma, but to test or measure the difference of the PBN parameter gamma for different particles. Okay, and this is the result before with GRB or with the FRB, and they prove something like the delta gamma should be something like in a value of 10⁻⁻⁻, something like this. Okay, and the period work is in the 1988 by Longo, and published in the Physics Review later, using neutrinos. And after some also Chinese scientists to use GRB and FRB to do this work. Okay, but all these tests have a simple but a flawed estimation. Because all the observed time delay are regarded as due to the destroy of WP. Maybe now some of this research to remove of the dispersion due to the interstellar medium, but of course this remove is not very accurate. Why? Because they did not know the time delay between the two different photons or two different neutrinos or two different photons and gravitational waves when these singulars radiated at the source, because GRB or FRB are very complicated to understand or to calculate the exactly intrinsic time delay over different photons with different energy. So they didn't know this intrinsic time delay, so they take all this observed time delay as a time delay due to the violation of the WP. Okay, so this will do, they use neutrinos or photons or use photons with different energy or time delay between the photons and gravitational waves, and even some work is use time delay between the gravitational waves with different frequencies. So all these are taken as the time delay is considered by the invalid of WP and ignoring the intrinsic delay at the source. Okay, but fortunately, we know exactly the intrinsic time delay of the gravitational wave with different frequency. And this because we have very good numerical relativity simulation, we have template theoretical templates based on post-neutrino theory and perturbation theory. So in principle, we know the time delay of the gravitational wave at 10 Hertz or 20 Hertz and the gravitational wave at 100 Hertz. Because here you can take that this is a different gravitational graviton with a kind of energy, and this another graviton with another energy. And if WP is valid, they will free fall in the universe with, at the same acceleration, and that will arrive on Earth at the same time. Not at the same time. The time delay will be keep the constants from the source to the Earth. Okay. So this is a waveform template we used to do the data analysis, and which we know this is a waveform template. Everybody should hear very familiar with this, and this is the phase of the gravitational wave. Now we add a dephasing on this phase due to violation of WP, because if WP is violated, different frequency with different gravitational waves with different frequency will have different arriving, the propagating time in the universe will be changed, and this will induce a dephasing of the waveform comparing with the general relativity prediction. Okay, so and also we can see, because in this work we mainly consider the potential from our galaxy, so we can see the capacity of the different source at a different position for the WP testing, and we can see that if we're very close to the center of our galaxy, we will get better constraint on the WP. And this is the 10 binary black hole events we use to do the testing. In the first work catalog, and the tools we use to to do the data analysis, mainly on the BBH. Okay, this is the estimated values of delta gamma for the 10 events, and we can see. Oh, be careful. This is the upper limit of delta gamma, not a measurement of delta gamma. Why? Because that in this data analysis or this work, we take all the time delay, or we take all the defacing as a violation of WP. Of course, it's not true because of how errors inside of the data and maybe other some things. So all this values is for the upper limit of the gamma. It means the delta gamma should be less than this value. So we can see this the result, and we cannot see they are coincide, because for GW 150914, and we can say, okay, the delta gamma should be less than 10 minus 10, and this one should be less than 10 minus, for example, 14. Okay, so we should take the best result for the gamma constraint. Okay, here we have 4 events have very good result, and first is this one, and this for 170104, and also here these 4 events, very good result. And this is the Fourier distribution of the gamma, and this one is estimated post-real distribution of the gamma for the GW 170104, and you can see the best value is at 10 minus 40. Okay, this is for another case. And this is the parameter estimation for the other parameters, for the mass, for the distance, and we can see that they are coincide with the LIGO result. And this is for GW 150914, and this is for another cases. And okay, and all these parameters are coinciding with LIGO in the error bar. So finally, the concurrence. I think I can say that okay, W is very important for the physics, and comparing with other observations, gravitational waves have uniform amounts for test WP. That is because we exactly know the intrinsic time delay when this gravitational wave radiated, and also we don't have the dispersion due to the interstellar medium, not like other electromagnetic signals. They will have some time delay come from dispersion from the interstellar medium. And our result imprints that WP value in cosmology scale at least for example, maybe, or at least for gravitational waves, 10 minus 40. And our results are most accurate for test W in cosmology scale, at least for gravitational waves. I hope more and more data, and especially, for example, during the Kagura data and other come in, and we can get more better and better constraint on WP. Thank you very much.